Hi friends, our next topic is coherent and incoherent addition of waves. Superposition principle says that at any particular point in the medium, the resultant displacement produced by number of waves is the vector sum of displacements produced by each of the waves. So when you want to calculate the resultant displacement at any point here, say, you want to take the phase also into account. That's what is the meaning of that statement. What is a coherent source? At a particular point, if the phase difference between the displacements produced by each of these waves does not change with time, then those two sources are said to be coherent. I'll explain you. Say at some point, the phase difference between these two waves is 2 pi, say, and at another point it may be pi, at another point it may be something, say, phi, random. It doesn't matter, but the condition is if it is 2 pi at some point, it should be 2 pi at all the instants of time. I mean, it should remain constant. At every point, the respective phases or the phase differences should be constant. Then the sources are said to be coherent or else incoherent. Say you have two coherent sources S1 and S2. For all the points P, where S1P is equal to S2P, what happens? Wave at P is given by wave due to the first source is A cos omega t. Then since the distance is same from second source also, y2 is also given by A cos omega t. So when I add them, y is equal to y1 plus y2, right? The resultant wave at point P. It will be 2A cos omega t. And you know that intensity is proportional to the displacement. So for this wave due to the individual source, the individual wave, displacement was A. So if I naught was the intensity due to each wave, then here it is 2A, right? The square of it will be 4A square. So A square corresponds to I naught intensity. 4A square should correspond to 4 I naught, right? So this will be the resultant intensity at that point P, and this is maximum in this case. So if two waves add to give this maximum intensity, that is known as constructive interference. Now consider the same situation, S1 and S2 coherent sources, but now you are calculating the resultant wave at some point Q, where S1Q is, say, some 7 lambda, that is 7 times the wavelength, and this is 9 lambda. What happens here? If y1 is A cos omega t, then y2 is given by what? The path difference is 2 lambda. That corresponds to a phase angle of 4 pi minus 4 pi. Since S2Q is longer, I have minus here. So the resultant will be y1 plus y2, right? And that is same as A cos omega t. And what is cos omega t minus 4 pi? It's nothing but the same. So I have plus A cos omega t again. What does it mean? I got the same result for these two waves which have path difference 2 times the wavelength. Take another case if you want, where say S1R is some 8.32 lambda and this is 9.32 lambda. Even here the path difference is lambda, right? So it will correspond to a phase angle of 2 pi. So even here you are going to get the resultant wave as 2A cos omega t, and hence constructive interference in both these cases also. What can I conclude? I can say that if my path difference is a multiple of wavelength, then I am going to get constructive interference, or even if the path difference is 0 also. So I can say that if my path difference S2P minus S1P is n lambda, where n is 0 or plus or minus 1 or plus or minus 2 and something like this, then I'm going to get constructive interference. Now consider this case where you have some point T, and here the phase difference S2T minus S1T is, say, minus 1.5 lambda, that is 1.5 times the wavelength. Okay, now what will be the V1 in this case? A cos omega t, say, and V2 or Y2, it will be A cos what? Omega t plus 3 pi. Got it? Because 1.5 lambda, that is 1.5 times the wavelength, corresponds to a phase angle of 3 pi, and cos omega t plus 3 pi is nothing but minus A cos omega t, right? So my resultant is y1 plus y2 is going to be 0. So since the amplitude is 0, my intensity, resultant intensity is also going to be 0. This is known as destructive interference. Similarly, destructive interference happens for those points whose path difference will be n plus 1 by 2 times of the wavelength, where n is 0 or plus or minus 1 or plus or minus 2 and something. We just discussed two cases, right? So let us try to generalize this, say an arbitrary point G, and let the phase difference between these two displacements at point G be phi. Phi may be anything, okay? So my y1 be a cos omega t and y2 at that point be a cos omega t plus phi. So my resultant will be y1 plus y2, right? It is a cos omega t plus cos omega t plus phi. There's a mathematical identity which says a cos a plus cos b is nothing but 2 cos a minus b by 2, that is phi by 2, into cos a plus b by 2, that is omega t plus phi by 2. So this will be my resultant. For coherent sources, at any point phi is constant, that is phi may vary from point to point, but given a point phi is constant, right? So this will be my amplitude and this is some cos angle. So intensity is proportional to amplitude, right? Amplitude square, right? So my net intensity should be proportional to 4a square cos square this phi by 2. If a square corresponds to I naught, my net intensity should be 4 I naught cos square phi by 2. So this is the resultant intensity, and this agrees with what we have done just now. For phi is equal to 0 or 2 pi or 4 pi, you get constructive interference, and for phi is equal to plus or minus pi or plus or minus 3 pi and so on, you're going to get destructive interference. Okay, what if your sources are incoherent? I mean, then this phi changes, right, for a given point also. Then you have something called as time averaged intensity, which is nothing but the average of these quantities. So you have to take the average of this thing. Since 4 and I naught are constant, the average of cos square theta will be 1 by 2, right? Because cos square theta varies from 0 to 1. So my average will be 4 I naught by 2, that is nothing but 2 I naught. This is the time averaged intensity for incoherent sources. What we have seen is interference with water waves, right? If you want to see the same interference with light waves, you have something called as Young's double slit experiment. Now, we want two waves, right? Two light waves. So, if we place one bulb here and another here, you are not going to see anything, because the light waves emitted by these bulbs undergo abrupt phase changes. But we wanted the sources to be coherent, right? So what Young did, he placed a light source here somewhere. So light from this bulb falls on both these slits. So if there is any change, phase change in this bulb, what happens? That is manifested in both these waves, right? Hence finally both these sources are coherent. And this is what you observe on screen. For all those points where constructive interference takes place, you have a bright fringe or bright spot. If there is a destructive interference, you see a dark spot. Now let's try to formulate this. What is the path difference for a random point P, which is at a distance x from the center? Say it will be S1P minus S2P. Okay, how to calculate S1P minus S2P? Let us use this one. We will start with S2P square minus S1P square. Okay, which will be S2P is what? D square plus x plus d by 2 whole square. This should give me S2P square, right? Because observe this triangle. This is d. This is x plus small d by 2, where small d is the distance between S1 and S2. So S2P square is the hypotenuse, right? Hence this should give me S2P square. And similarly I have S1P square as d square plus x minus d by 2 whole square. Hope this is clear. Which is equal to 2xd. Now S2P square minus S1P square can be written as S2P minus S1P into S2P plus S1P, right? So I'll write 2xt by, I'll write the other term here, s2p plus s1p. Observe one thing. If my capital D, the distance between the two slits and screen, is very large than x as well as small d, then I can approximate the denominator to 2 capital D. That is the assumption we are making. So finally I have the path difference as x d by d. If my path difference is equal to n times wavelength, we see that there is constructive interference. So if n lambda is equal to x small d by capital D, my x will be n capital D lambda by small d. So for all those points which are at a distance n lambda capital D by small d at this distance from the center, there you will get bright fringe. So similarly, when there are points which are at a distance n plus 1 by 2 into capital D lambda by small d, at these points you are getting dark fringes. Of course, n is equal to 0 or plus or minus 1 or plus or minus 2 and so on. Now, the distance between two consecutive dark or bright fringes or bands is known as the fringe width, which is equal to d lambda by d, and it is denoted by beta. Actually, a particular fringe would correspond to the locus of points which have constant value of path difference, right? So when you have two slits, this is your interference pattern, right? If you had two point sources, then actually it would have been a hyperbola. And when capital D is very large, then you can approximate it to be the central part of this, which is nothing but this diagram. So finally, Young's experiment was the first proof of the fact that light added to light can not only produce more light but also darkness. Interesting, right? Observe this. This is the fringe width, right? D capital lambda capital D by small d. So when you increase the distance between these two slits and the screen, when you increase capital D, your fringe width is also going to increase. But there is something called as lambda by d, that is the angle subtended by each fringe. This is the angular separation between fringes. This is not going to change with change in capital D. When you replace your source with another source such that your wavelength changes, then both fringe width as well as angular separation between fringe, both of these are going to change. If small s is the size of the source and capital is the distance between source and the two slits, capital S is this, there is a condition that this should be less than the wavelength by separation between the slits. If this is not satisfied, you are not going to see any fringes. So if S is decreased, or that means if source is both near to the slits, or if D, small d is increased, that is both the slits are moved far away, both of them result in either the decrease of this term or increase of this term, and hence this inequation is less satisfied in that case, and that results in blurred image or not so sharp image. What happens if you use white light instead of monochromatic light, that is as a source? This is what you observe when you use monochromatic light. When you use white light, all the individual wavelengths follow the same fringe pattern, but the fringe length corresponding to each wavelength would be different. Since the central point is having zero path difference for all the wavelengths, you will get a bright fringe there, and you have different fringe lengths according to the wavelength. Whenever you have two or three colors at some point, they get added and you see the resultant color. This is what you observe when you use white light, and that's it for now. Keep watching. In the next video, we'll discuss about diffraction.